kind introduction. First of all, I'd like to deeply thank the organizer for the kind invitation to this great Congress of India. And in this talk, I'd like to talk about organoboron electrolyte for enhanced performance for energy and sensing applications. And first, briefly, I'd like to introduce about our institute, JAIST, Japan Advanced Institute of Science and Technologies. And our institute, JAIST, is located in the central Japan area, in the west coast side. And our location is a very convenient place, and we have easy access to the main city of Japan, like Tokyo, Nagoya, and Osaka. And just very recently, our area was connected with Tokyo by Super Express, and now frequently it's possible for us to do one-day trip to Tokyo and Osaka and many main cities of Japan, so conveniently. And our institute is the first independent graduate school of Japan. So this means we do not have undergraduate courses. And we have the three departments of the information technology, knowledge science, and materials science. And in Japan, we have the highest percentage of international students, and more than 50% of our students are from outside of Japan, and we have fully bilingual programs, so students can get enough credit even without any Japanese language skill at all. And we have active relation with many Indian institutes. So we have MOU with University of Delhi and IIT Madras, IIT Gandhinagar, and recently also have with IISc as well. And very recently, the EU multi-rank started by EU ranked our institute as a second institute of Japan in the category of the research activity of faculty staff. And our research group member, also half of our members are Indian students. So we are almost a Japan-India nanocomposite research group. And our research project is mainly on electrolyte interface design on lithium-ion secondary batteries and photoelectrochemical water splitting and fluoride anion sensing, and also working on oxygen reduction and so forth. And the first is just a brief general introduction on lithium-ion secondary batteries. And nowadays, in worldwide, lithium-ion battery has been so widely investigated, and due to their many desirable characteristics like high potential, very high energy density, and their application, as you know, ranged from mobile electronic devices, automotive applications, backup system for natural energy like solar energy and so forth. And however, the problem associated with lithium-ion electrolyte today is a very low lithium transference number, and also insufficient electrochemical window, and also safety is the greatest concern among consumers, and due to the flammability of the electrolyte materials, even now many of explosion accidents has been reported frequently. In this talk, I'd like to focus how we can make approach to these problems, mainly by utilizing organoboron chemistry. And till now, as the most common solid polymer electrolyte, polyether derivatives has been so widely investigated. And however, in spite of their moderate ionic conductivity, their lithium transference number, I mean the selectivity of lithium cation transport, is generally very low at ambient temperature due to the strong binding of ether oxygen to lithium cations. And as a result, generally the lithium transference number is only at most 0.1 or 0.2 at ambient temperatures. So we developed an idea like a boron incorporation to the polymer should be the attractive, promising approach to enhance the selectivity for lithium cation transport. And after introduction of tricoordinate boron in the main chain of polymer electrolyte, in the presence of lithium salt, boron had trapped an ion efficiently and thereby enhanced the selectivity for lithium cation transport. And on the other hand, after the polymer reaction of organoboron polymer with the organolithium reagent, the anionic charge was immobilized on the polymer chain, and this also led to the very much enhanced lithium transportations. And under such concept, till now we have developed various kinds of the organoboron polymer electrolyte bearing a variety of the organoboron structure like boric esters, alkyl borane, and lithium borate, and boron stabilized anion, and so forth, and studied the structure property relationship in details. And particularly the alkyl borane based material was found to show very high lithium transference number of over zero point 0.5, and found to be a very efficient kind of electrolyte, particularly in terms of selectivity of lithium cation transport. And such a strategy was also successfully extended to the ionic liquid. And these days, ionic liquids are also being studied vigorously as an alternative electrolyte that will be more suitable for the more safer battery systems due to the non-flammability and non-volatility of this kind of electrolyte. However, the selective cation transport is not so facilely achieved in this class of electrolyte either, because in such systems, the component ion of ionic liquid also tend to migrate under the potential gradient. To enhance the lithium transference number, we developed various kinds of organoboron ionic liquid, in which the ionic liquid moiety and boron moiety were covalently tensile. And recently also we have developed one organoboron ionic liquid showing relatively high ionic conductivity and high lithium transference number at the same time. But so far we have we had been working on this kind of approach because for most of the systems, ionic liquid was not miscible with boron compounds. So we have very recently we studied systematically on the miscibility of ionic liquid with various kind of anion receptor boron compound. And as expected in the initial attempt, for the under most of combinations, the mixture of ionic liquid and boron was not miscible, and immediately after mixing, the immediate phase separation was observed in naked eye. However, we found that only under specific combination of the imidazoline TFSA type ionic liquid and methyl dimethoxyborane, the homogeneous solution was readily obtained. And this type of the binary electrolyte showed a significantly lower viscosity when compared with ionic liquid itself. And due to such a low viscosity, it showed a very good ionic conductivity. And more importantly, these binary electrolytes showed extraordinary high lithium transference number. And for instance, the mixture of butyrylmethylindazoline TFSA with methyl dimethoxyborane was found to show that almost 3 times higher lithium transference number when compared with ordinary ionic liquid itself. And we also studied the property of 1 to 2 volume mixture and 1 to 3 volume mixture as well. And as you see, the 1 to 2 volume mixture shows the best result. And in this case, ionic conductivity of exceeding 10 to the minus 30 Gs per centimeter, along with the extraordinary high lithium transference number of 0.86 as a liquid electrolyte. And to investigate the electrochemical stability of this electrolyte, we measured the linear sweep voltammogram of this electrolyte and found to show the approximately 4 volt of the potential window and indicating their suitability for the use and the commercial combination of electrode materials. And very recently, we also found that FSA type ionic liquid was also miscible with methyl dimethoxyboron. And in this case, in addition to the even wider potential window, the lithium transference number was found to exceed zero point 0.9. And also the ionic conductivity was also exceeding 10 to the minus third Siemens per centimeters. So by utilizing this electrolyte, we have fabricated the lithium-ion battery composed of lithium foil electrolyte and the silicon anode materials. And as you see, the reversible charge and discharge profile was observed, and maximum discharging capacity reached approximately close to the 3000 milliampere per gram. And interestingly, with increasing the number of cycles, gradual increase in the discharging capacity was observed possibly due to the formation of a fairly conductive surface layer, SEI layer on the electrode surface. And the next topic is the boron incorporation to the ion gel electrolyte. Sorry. And the design of the organic-inorganic hybrid electrolyte is a promising approach in designing the highly non-flammable and thermostable electrolyte. And here, such a class of material was successfully prepared by means of the in situ sol-gel condensation in the presence of the low viscous ionic liquid. And sol-gel condensation was carried out for the tetramethoxysilane and alkoxybolane in the presence of catalytic amount of hydrogen chloride. And after 1 week of reaction at 60 degrees Celsius, the condensation was almost completed, and successfully the desired material was obtained, and a wide range of materials composition. And particularly when the additive was lithium TFSA, generally the transparent materials were obtained. On the other hand, when lithium PF6 was added, generally the only target materials were obtained. And the SEM image shows that the lithium TFSI based system is showed the fairly homogeneous texture, showing the very small phase separation orders. And on the other hand, lithium PF6 based system showed the discoidal profiles, indicating a higher order of phase separations. And such a morphological difference had largely affected both on the ion conductive behavior and the thermal behavior as well. And for instance, in the case of lithium PF6 based systems, a fairly high ionic conductivity was observed, possibly due to the better connection of ion conductive paths and a higher degree of higher order of phase separation. And on the other hand, in terms of thermal stability, the TFSA based system showed a much higher thermal stability, indicating that homogeneous mixing of organic and inorganic moiety is highly important in achieving such a high thermal stabilities. And next, the flammability test was also carried out. And when commercial electrolyte was exposed to fire, it immediately caught a fire. However, when our material was exposed to fire, even after 1 minute of treatment, it did not catch fire at all, and only color changes were observed and had shown self-extinguishing features. And by using such kind of the non-flammable solid electrolyte, we tried to fabricate the lithium-ion battery. But in the initial attempt, no successful charge discharge was observed. So we tried to optimize the charge discharge condition utilizing dynamic electrochemical impedance spectroscopy (DEIS) technique. And here, DEIS is not a mere in situ impedance measurement during the charge and discharge, but at each point of in situ impedance measurement, external DC potential was superimposed to the battery cell to enable the same state of charge with actual battery cells. So in this manner, we measured for the behavior for one of the anodic half cell fabricated, and we had obtained this kind of profiles. And from this profile, you can see that when potential grows higher than 1.5 volt, for the first time, some tails grow due to the interfacial resistance. So this indicates the cutoff potential should be set at 1.5 volt. And after revising the cutoff potential accordingly, we observed the highly reversible and beautiful charge discharge profiles. And in this manner, we have attained the successful charge discharge utilizing the non-flammable and solid electrolyte systems. And the next topic is a low molecular weight organoboron solid electrolyte. And nowadays, in the field of the solid polymer electrolyte, till now many researchers had pointed out the theoretical limitation of their ionic conductivity, and they say that as long as the ionic motion is dependent on the segmental motion of polymer chain, such kind of the ionic transportation can never exceed the diffusion rate of low molecular weight counterpart. So many researchers are trying to facilitate their ionic transportation in solid state by introducing some structural order to ion conductive pathways. For instance, some Japanese researchers tried to introduce a liquid crystalline smextic A layer to the ionic liquid-based systems. And as a result of such a dimensional control of ion conductive paths, the significant enhancement of conductivity has been observed. And on the other hand, Kitagawa et al. Reported the morph-based proton conductive channels. And on the other hand, now we are trying to utilize the crystalline boron compound as a scaffold for ion conductive paths through boron anion interactions. The crystalline boron compound was prepared by dehydrocoupling between ethylene glycol and methylborane, and the resulting compound was purified by the decrystallization to afford the needle-shaped crystals. And their structure was confirmed by proton and boron-11 NMR spectra, and to this compound, the lithium salts were inserted by two different methods. And the first method was doping by conventional method, in which both the boron compound and lithium salts were dissolved in the organic solvent, and after mixing, organic solvents were removed under reduced pressure. And the second method was doping by solid-state grinding without using any solvent. And in this case, solid-state grinding was carried out under inert atmosphere. And interestingly, the samples prepared by the solid-state grinding showed fairly high values when compared with the sample prepared by conventional method. And also, such enhancement was observed only under specific composition of boron and lithium salt. And under such composition, we found the activation energy of the ionic transportation was found to be very low under such compositions, and indicating that the presence of the solid-state crystalline boron compound is fairly important in achieving such a great enhancement of conductivities. And this solid electrolyte shows a lithium transfer number of around 0.28, and after adding some EC and DC, the potential window wider than 5 volt was obtained, and this is indicating their suitability for the use and more advanced type of electrode materials. And after fabricating lithium-ion batteries composed of lithium foil, electrolyte, and graphite, the successful charge and discharge was possible under this all solid-state systems. Okay, and the final topic is the silicon boron dual inorganic elements type copolymers for fluoride anion sensing applications. And so far, by utilizing a hydroborane precursor, we have developed various types of the conjugated materials. For instance, we developed a pi-conjugated organoboron polymer in which pi conjugation length is extended through the vacant p orbital of the boron atom. And this material showed the intense blue light emission, very high the third nonlinear optical susceptibility, and became commercial from the Sigma Aldrich Corporation of the United States. And after that, we also developed organoboron polymer electrolyte, and this second scheme of material had shown the lithium transference number of the 0.89, and as far as we know, it is the highest among the anion trapping type electrolyte ever reported. And here I'd like to introduce one another interesting materials based on a new mode of conjugation, that is sigma p conjugation. And so far, many kinds of conjugated system is known, like a pi conjugated system, sigma conjugated system, sigma pi conjugated system, sigma p pi conjugated system. So here, for the first time, sigma p was developed by us. As a basic concept is that in the case of ordinary sigma pi conjugation, when aromatic moiety is photoirradiated, the original pi level is excited to pi star level, and to the original pi level, the d electron flows. However, in the case of sigma p, due to the inherent p orbital on boron atom, such a conjugative interaction happens even at the ground state. So such kind of polymer was for the first time prepared by dehydrocoupling reaction between the phenylsilane and methylborane. And okay, I'll skip this slide. And the DFT calculation also indicates that with increasing the chain length of the p-pi conjugation backbone, the good marked decrease in the band gap was observed, showing that pi conjugation, p-pi conjugation is prevailing in this system, and this was found to be very efficient for the Tannon-type fluoride anion sensing towards the micro-order scale concentration of the fluoride anions. And this is as a novel mode of the conjugation materials. Recently, it was highlighted in the RSC polymer chemistry as cover images. Okay. And final topic is the novel polyborosiloxane. And this polymer is also a novel materials. And this polymer is also found to show the very high sensitivity to the fluoride anions. And as you see, this polyborosiloxane is found to show the sensitivity to even to the 10 to the minus 10th molar concentration of the fluoride anion in aqueous systems. And as far as we know, that this is showing the lowest detection limit for fluoride anion ever reported. And DFT calculation can indicate that in this polymer structure, boron has been exported to the outside of the polymer chain. So such conformation should be responsible for such extraordinary high sensitivity to fluoride anions. Okay, finally, I'd like to summarize my talk as follows. And thank you very much for your kind attention. And I wish you all of you a happy new year for year 2017. Thank you very much.